Hi everyone. In this module, we are going to learn the applications of conductometry. This is analytical chemistry, MSc, first semester's soft core paper SCT 101. In this unit, we learn the concept of degree of dissociation of weak electrolyte and its dissociation constant, ionic product of water, solubility and solubility product, sparingly soluble salt, conductometric titration, applications of gravimetry, applications of colorimetry, and some important applications of colorimetric titrations. The objectives of these units: to determine the value of many physical qualities, means degree of dissociation, dissociation constant of weak electrolyte, ionic product of water, solubility product principle, describes the various applications of conductometric titration, electrogravimetric methods in analysis of various metal ions, types of conductometric titration, and applications of colorimetric titration. Here, what are the applications of conductometry? Generally asking in that 2 mark questions. In that previous units, means unit 9, we discussed the theoretical and practical aspect of conductometry. We have said that the conducting ability of electrolytic solution provides a direct proof of the existence of ions in solution. Generally, from this application, we have to determine the many physical quantities such as degree of dissociation, dissociation constant of weak acids and bases. The degree of dissociation of weak electrolyte. The conductivity values can be used for calculating degree of dissociation. Consider a weak acids like Ha. The equilibrium state is represented in this Ha, it is reversible, H plus A minus. The initial concentrations of Ha is C. There is no formation of any ions. At equilibrium concentration, the alpha is the degree of dissociation. That's why at equilibrium concentration, the concentrations of Ha is C into 1 minus alpha. What about that? H plus and A minus is equal concentration C alpha and C alpha. The equilibrium constant in theoretically it is written as alpha H plus alpha A minus by alpha HA. All the values are known here. H plus A minus here HA. Finally, Ka, degree of dissociation constant of weak acid is equal to alpha square C by 1 minus alpha. Actually, this equation is termed as Ostwald's dilutions law. Similarly, we consider weak base BOH. It dissociates to formation of B plus and OH minus according to this Arrhenius theory. The substance which dissociates OH minus, that is called what? Base. Initial concentration of BOH is C. At equilibrium, the concentrations of BOH is 1 into C into 1 minus alpha. The concentrations of B plus and OH minus is C alpha, C alpha. Here, where C is the concentrations of the base, alpha is the degree of dissociation. Here, Kb is equal to alpha square by 1 minus alpha. Now we consider a partial dissociation constant of salt Ma, that is low solubility, and its equilibrium state can be written as Ma gives M plus and A minus. Here Ma is the form of pure solids, that's why alpha Ma is equal to 1. Next we consider here some molar conductivity values of nitric acids in methanol. This is the molar conductivity values of nitric acids in methanol. This table is not required for your examination. This is the graph. Next we consider ionic product of water. The water containing a certain proportions of hydrogen and hydroxyl ion. Here H2O is undergo dissociation to formation of H plus and OH minus. The ionic product of water is written as alpha H plus and alpha OH minus. This is ionic product of water. In that ionic product of water, the conductivity of pure water is 5.8 into 10 to the power of minus 6 Siemens per meter at 298 Kelvin and means 0 degrees Celsius. We can calculate concentrations of C by substituting their values in that equation. What we are getting finally here 1.12 into 10 to the power of 14 mole per dm cube square. This is the ion conductivity and ionic product of water are mentioned here. That solubility and solubility product of sparingly soluble salt. We consider any salt in that solvent that is undergo either sparingly soluble or completely dissociated. The conductivity of a saturated solution of a sparingly soluble salt can be determined by subtracting the measured conductivity of the pure solvent from the measured conductivity of the saturated solution. Here where C is the concentration, since the salt is sparingly soluble, its solutions can be considered to be infinitely dilute and we can replace molar conductivity with limited molar conductivity of the salt. Next we will move on to that conductometric titration. It is one of the very important titrations in the point of examination. The principle of conductometric titration is based on the fact that during the titration, one of the ion is replaced by other, and invariably these two ions differ in the ionic conductivity, with the result that conductivity of the solution varies during the course of titration. The equivalence point may be located graphically by plotting the change in conductance as a function of the volume of the titrant added. Means that in that analyte that is constant, just we are going to variations of that titrant. After the plotted graph, volume of the titrant added was that equivalence point, what we are getting conductometric graph here. Here, what are the rules to find useful? The smaller the conductivity of the ion which replaces the reacting ion, the more accurate will be the result. Thus, it is preferable to titrate a silver salt with lithium chloride rather than with hydrochloric acid. Generally, cation should be titrated with lithium salt and anions with acetate, as these ions have low conductivity. In the larger the conductivity of the anion of the reagent which reacts with the cations to be determined. The titration slightly ionized salt does not give good result, since the conductivity increases continuously from the commencement. The salt present in the cell should be virtually completely dissociated. Next, the intercept of keeping V is small, means volume is small. The reagent for the conductometric titration is ordinarily several times more concentrated than the solution being titrated. A microburette may then be used for this volumetric measurement. It is one of the very important titrations regarding your point of examination, the conductometric titration. Now we are going to explain that what are the typical conductometric titrations of titration. A strong acid with a strong base. In that strong acid we have to take here HCl, strong base here NaOH. Before sodium hydroxide is added, the conductance is high due to the presence of highly mobile hydrogen ions. When the base is added, the conductance falls due to the replacement of hydrogen ions by the added cations such as H plus react with that OH minus to form undissociated water. This decrease in conductance continues till the equivalence point. This is the point of this equivalence point. Again we have to add that sodium hydroxide. At the equivalence point, the solution contains only sodium chloride. After the equivalence point, the conductance increases due to large conductivity of OH minus ion. Initially, we are adding sodium hydroxide, H plus ions present in that acid. Here, when we are going to add OH minus, it undergoes neutralization till equivalence point. After that, it increases the conductance because the concentrations of OH minus ions increases. Next, the second one, weak acid with a strong base. We have to take an acetic acid is a weak acid with a strong base means sodium hydroxide. Initially, the conductance is low due to the friable ionization of acetic acid on the addition of base. There is a decrease in conductance not only due to the replacement of H plus by sodium plus, but also suppress the dissociation of acetic acid due to common acetate ion. That's why that is also it undergo neutralization. The third type of conductometry, strong acid with a weak base. Sulfuric acid is a strong acid, ammonia is a weak base. Initially the conductance is high. Just you see the graph. then it is decreases due to replacement of H plus ion. But after the endpoint has been reached, the graph becomes almost horizontal. Since the excess aqueous ammonia is not appreciable ionized in the presence of ammonium sulfate. In weak acid and weak base, the nature of the curve before the equivalence point is similar to the curve obtained by titrating weak acid against strong base. After the equivalence point, the conductance virtually remains same as the weak base, which is being added is friably ionized and therefore it is not much conducting. Here like that this graph is obtained. Next, what are the mixtures of strong acid and a strong acid and weak acid and a strong base and a weak base? It is a mixture with two different types of acids and two different types of base here. In this curve, there are two breakpoints we observed here. Here, the first breakpoint corresponds to the neutralization of strong acid. This is what? Neutralization of strong acid. When the strong acid has been completely neutralized of weak acid and after the conductance increases due to the excess of OH minus ions in case of strong base as the titrant. However, when the titrant is a weak base, it remains almost constant after the endpoint, similar to what? Titrant only. Here first it breaks the strong acid, again it increases the concentrations of OH minus ions, that weak acid it undergo neutralized, again keep on adding that base. Here concentrations of sodium hydroxide increases, OH minus ions is also increases. Next, what is meant by displacement or replacement titration? In this concept, we have to take weak acid titrated with strong acid. The anion of weak acid is replaced by strong acid and weak acid itself is liberated in the undissociated form. Similarly, in the addition of strong base to the salt of weak base, the cation of the weak base is replaced by that of the stronger one and the weak base itself is generated in the undissociated form. For example, we have to take a strong acid HCl is added to sodium acetate. The curve is observed like that. The curve is observed like that. Here, this is what? Strong acid. This is weak acid. This is strong base. This is weak base. Generally, the conductance curve is appears like that. Here, keep on adding into that sodium hydroxide into that strong acid. Initially, it breaks the strong acid. Again, it is continuous. It breaks the weak acid because it is undergo undissociated form. Keep on adding into that sodium hydroxide. Here, the ammonium chloride and sodium hydroxide is also, it increases gradually. Next, precipitation titration and complex formation titration. I think you know that precipitation titrations in the part of practical classes, that precipitation titrations generally be done in that practical classes. Precipitation titrations means the reactions may be made the basis of a conductometric precipitation titration, provided the reaction product is sparingly soluble or is a stable complex. Here, the solubility of the precipitate should be less than 5%. The addition of ethanol is sometimes recommended to reduce the solubility of the precipitation. Here, some examples generally we are going to take an ammonium sulfate in aqueous ethanol solutions with barium acetate. If the solubility of the precipitate were negligibly small, the conductance at the equivalence point should be given by AB and not the observed AC. The addition of excess of the reagent depresses the solubility of the precipitate, and if the solubility is not too large, the position of the point B can be determined by continuing a straight portions of two arms of the curve until they intersect. Just you see that these type of reactions are very important in the point of examination. The precipitation titration, the complexometric titration, okay, like that. Just you see that the graph of this precipitation titrations with a conductometric value. Here the slow rate of precipitation, particularly with microcrystalline precipitate, prolongs the time of titration. Seeding or the addition of ethanol may have favorable effect. That oxidation reduction titration, simply that is called what? Redox titration. The conductometric method is not well suited to the study of oxidation reduction titration. Almost all such reactions must be carried out in the presence of large excess of acid or base, which more or less completely masks the change in conductance due to the redox reaction. A typical example is the titrations of Fe2 with potassium permanganate, in which, say, a 0.01 molar solutions of Fe2 plus in 0.5 molar sulfuric acid is titrated with 0.02 molar potassium permanganate. Here, that stoichiometry, that is experimental evidence only. Why we are going to take in 0.01 molar Fe solution and 0.5 molar sulfuric acid, 0.02 molar potassium permanganate. These are all what experimental evidences. That's why for that theory aspect we are going to take as it is. Next, what are the applications of this electrode gravimeter? Here already we discussed in that theoretical and practical aspect of electrode gravimetry, that unit 5. In these methods, electrolytic precipitation or electrodepositions of various metal ions from complex solution is carried out under suitable condition on weight, cathode or anode, and the increased mass is determined. There are two types of electrogravimetric methods. One is what? Constant current electrolysis. Simply that is electrogravimetry without potential control. In this case, electrodeposition is carried out by keeping the current constant and applied potential is increased periodically as the electrolysis proceeds. The constant potential electrolysis, simply that is called what? Controlled potential electrolysis. This electrogravimetric method is also called a potentiostatic method. In this method, potential of the working electrode is maintained at a constant level versus a reference electrode. We consider SCE, okay, standard control electrode. This technique requires additional equipments like electronic voltmeter, a potentiostat and a reference electrode. These are all some examples regarding to that constant potential electrolysis or controlled potential electrolysis. These are all some values. What are the analyte? What are the cathode and anode? Generally, we have to use to which condition? This is the AC plus. The cathode is platinum, anode is platinum. Here, in alkaline, Cn minus solution generally. What are the separations of this? Electrogravimetry can be used to separate one species from another in solution by selectively plotting it out and removing it from solution. This method is used to remove interference, particularly in electrochemical methods. The controlled cathode potential gravimetry is very useful in the separations of quantitative determinations of metallic species. How to prepare that preparative organic chemistry? In an organic, compounds can undergo series of reductions, each at a definite potential. It is then possible to reduce the starting material to the desired product by controlling the potential of the cathode during reduction. The type of electrolytic reduction is much more economical than chemical reduction, where side reactions produce undesired products. These are all some important work regarding that. What is the role of the tartarate in analysis of the sample having copper, bismuth, lead and tin? Write the limitations of electrogravimetric. Next, electrolytic determinations of organic compounds. By controlled potential colorimetry offers a new step for the electrolytic determinations of organic compounds. Trichloroacetic acid and picric acids are quantitatively reduced at a mercury cathode. The colorimetric methods permits the analysis of these compounds with an accuracy of 0.1%. That is electrolytic synthesis of new organic compound. The synthesis of new species and novel chemical compounds are possible. No chemical reagents are required since electron itself is the reagent for carrying out these reactions. No contaminations of the products takes place. Now we are going to come into the very important point, applications of colorimetric titration. That colorimetry as a controlled potential as limited application. Here with colorimetry at controlled constant current range of substance that can be determined by continuously increasing. The technique can be safely applied even in those substances which do not react quantitatively if a substrate weight is generated quantitatively at the electrode with 100% current efficiency. The quantity of substances reacted is calculated with the Faraday's law. The quantity of electricity caused can be emulated simply from the time of electrolysis at constant current. Okay. Just to go through that, these are the very important applications of this colorimetric titration. The colorimetric titrations have been developed almost for all types of colorimetric titration. That neutralizations, titrations mentioned here. Neutralizations means the formation of that pH is equal to 0 here. The titrations of strong acid or weak acids with hydroxide ion generated at the cathode. Here is the one of the main advantages of this colorimetric titrations of acids. It is difficult associated with the presence of CO2 in the test solutions or carbonate in the standard titration space are easily avoided. Carbon dioxide can be removed complicity from the solutions by passing nitrogen gas before the titrations is commenced. The presence of any substrate that is reduced more easily than hydrogen ion or water at platinum cathode or which is oxidized more easily than water at platinum anode with the interface. The precipitation and complex formation titration. This is also very important, asking in that 5-mark question. A large number of colorimetric titration have been developed in the literature. This is the anode generations of Ag plus ion. The generating electrode consists of a heavy silver wire and a cell of the type as shown in the figure. Here, we have to take here AgCl as an example. AgCl with 25 to 50% of ethanol must be added to lower the solubility of silver chloride. The chloride, bromide, iodide are the best determined with mercury generated with 100% efficiency from mercury coated gold or from mercury pool anode. The endpoint is determined potentiometrically. In the titrations of chloride ion, addition of methanol is essential in order to reduce the solubility of mercury chloride. Next, oxidation reduction titrations. For that, here this is the repeated. So many times we are going to repeat that acid base titration. What are the advantages of this colorimetric titration? It is very easy to handle small quantities of reagents by colorimetric titration. By proper choice of current, micro quantities of substance can be analyzed with greater accuracy and ease. A single constant current source can be used to generate precipitating, complexing and redox reagents. Colorimetric titrations can readily be added to automatic titration as the current control is easily done. A number of automatic colorimetric titrators are readily available in the market to monitor environmental pollutant. In chloride titrator, silver ion is generated colorimetrically. The sulfur dioxide monitors analytically generated bromine oxidizes the analyte to sulfate ions. In carbon dioxide monitors, in which the gas stream absorbed in monoethanolamine is titrated with colorimetrically is generated. In water titration, corn fissure reagent is generated electrolytically to determine trace level concentrations of water constant or merge. These are all important questions and summary of this. These are terminal questions. You go through that. Some numericals and all. Next, unit 11, potentiometer. We learned the concept of colorimetry in that previous slides. Now we are going to discuss the unit 11, potentiometer. From this unit, the objectives are the principles of a potentiometric method and operations of a potentiometer, describe some common types of reference and indicator electrodes, calculate the equilibrium constant from cell potential, describe chemical reactions involved in potentiometric titration, explain the principle of potentiometric titration, state the experimental details of neutralization, redox, precipitation and complexation reaction. That potential means, consider that Nernst equation which we have studied in that previous unit. You have seen earlier when a metal is immersed in a solution containing its own ions. Say zinc rod in zinc sulfate solution, a potential difference is established between the metal and the solution. The potential difference E for an electrode reaction can be given by Nernst equation, where R is gas constant, T is absolute temperature, F is Faraday's constant, N is the valency of ions, AMN plus is the activity of ions in the solution, and E naught is a constant depending upon the metal. So that is the abbreviations of the Nernst equation. Next, this is the reformed Nernst equation. E is equal to E naught minus 0.0591 by N log 1 by Amn plus. Here R value, T value, Faraday's constant value are mentioned here. How to measurement of potential? The EMF means electromotive force developed by a galvanic cell. That is cannot be measured accurately by placing a simple D voltmeter across the electrodes, because a significant current is required for operation of the meter. Since current is drawn from the cell, a variation in concentrations of the reacting species will take place, which leads to change in the cell voltage. An additional factor is the development of ohmic potential drop due to the internal resistance of the cell. This opposes the potential due to the two electrodes of a galvanic cell. A truly significant value for output of a cell potential can be attained only if the measurement is made with a negligible passage of current. The potential measurement with potentiometer is the theory based on that, which you consider in that circuit diagram for laboratory potentiometer. The potentiometer, it consists of that watt, here current is the resistance, here linear voltage divider is the Western standard cell, which is a key. Okay, this is current detector. Just we see that the schematic diagram of a simple potentiometer. To understand the functioning of the instrument, it can be divided into two parts: a voltage divisor and galvanic cell part. The working battery with potential EB is connected to the terminal of a linear voltage divider EB. The electrical resistance RAC from one end A to any point C is directly proportional to the length AC of the resistors. That is, RAC is directly proportional to AC. Where K is what? Proportionality constant. Here some G is the, that is sensitive galvanometer. All are that is placing in that in series port. What are the basic principle of this? A current I flows continuously from the battery through AB, causing a potential drop between A and B. From that Ohm's law, E is equal to IR. By current passing between A and C is also current is given by the potential drop between A and C. Here EAC is equal to I into R is. The resistance along resistors is linear. The above can also be written as. This is the equations for that. Now there are three possibilities exist if the potential divider is adjusted to a position of EAC and the key K is pressed. Two of these are when EAC is greater than EX or ES. Electrons will be forced to flow from right to left through the unknown cell, and the direction will be reversed if EAC is less than EX. The third case is where EAC is equal to EX. That third case, EAC is equal to EX here. And for this situation, no current flows through the galvanometer and galvanic cell. The entire explanation is based on this diagram. This diagram with that from Ohm's law only we developed. Just be carefully you go through that. Here EX is what? The unknown potential of the cell will be obtained by measuring the two distances with cell of unknown potential and known EMF of the cell. What is meant by standard cell? The previous subsections, you have seen that there is a need of standard source of potential for the measurement of potential of unknown electrolytic cell. The most commonly used standard cell in potentiometry is the Weston cells, means Weston cadmium cell, which is depicted in the following figure and can be represented by cadmium sulfate and mercury sulfate in mercury. Here cadmium mercury represents the solutions of cadmium in mercury. The two half cell reactions occurring is as follows. Here cadmium it liberates electron. The mercury it gain of electron, means it undergo both oxidations and reductions to formation of that EMF well. This is the Weston cadmium cell. This is the cadmium amalgam. This is mercury sulfate. This is cadmium sulfate crystals. This is a saturated cadmium sulfate solution. The direct potentiometry. The potentiometric methods of analysis may be grouped into direct reading method or direct potentiometry and potentiometric titration. In this section, we are taking up direct potentiometry in detail. In subsequent section, the potentiometric titrations will be discussed here. The direct potentiometry is the method which makes use of the single measured electrode potential to determine the activity of the ions of interest. In this method is widely used for determinations of pH of the solution. In that electroanalytical method, the two electrodes are required. The potential of one of the electrode is known and the constant is completely independent of the composition of the solution. Here, one is the reference electrode and another one is that constant electrode. Here, the junctions is formed between that. Here, the direct potentiometric measurement, the potential of the cell can be expressed in terms of the potential developed by the indicator electrode, and the reference electrode is mentioned. E cell is equal to E indicator and electrode potential. Reference electrode plus E cell means junction potential. Consider the indicator electrode whose potential vary with cations, activities or concentration. We can write Nernst equation. Generally we return this is indicator electrode and the Nernst equation. This is a cell electrode. The overall rearrangement, what we are getting this one. Finally, we are getting PA is equal to minus log En plus is equal to N into E cell minus K by 0.0591. Where Pm and Pa are the negative logarithm of the metal ion activity Amn plus and An plus respectively. These terms are more general form of the familiar terms pH. K is the summation of several constants, including standard electrode potential of metal ions or anion, potential of reference electrode, junction potential, a symmetrical constant if membrane electrode is involved. All direct potentiometric methods are based on equation. The above equation. Both the equations in terms of E cell. This is what E cell reactions. This is the graph with respect to that Pm versus E cell and Pa versus E cell. Okay, let's go through that. Next we will move on to that reference electrode. That reference electrode, some importance are there. The potential of the electrode should remain constant, even some current is passed through it. The potential should be reproducible. The electrode should be easily prepared from readily available materials. The potential of the electrode should not change with temperature, and it should not be cheap. These are all what's some important of this reference electrode. Reference electrode is needed to measure the EMF of other solution. What are the important reference electrode? That is standard hydrogen electrode. Because that standard hydrogen electrode, that EMF value is 0. That's why that is used as a reference electrode. With the help of this standard hydrogen electrode, we are going to determine the EMF of other electrode. This is what standard hydrogen electrode. The standard hydrogen electrode is constructed with the help of platinum electrode. That is dipping into that 1 mole per dm cube of hydrochloric acid solution. The pure and dihydrogen gas is passed into that. The H plus ions is coated on that platinum electrode. The platinum electrode is act as an what? Standard hydrogen electrode. In that standard hydrogen electrode, the EMF value is equal to 0. Hence, that is used as a what? Reference electrode to measure the EMF value of other metal electrodes. That calomel electrode. That calomel electrode is the most widely used electrode due to its ease of preparations and constancy of potential. A calomel oxide is one in which mercury and calomel are covered with aqueous potassium chloride solution of definite concentration. What is the concentrations of that KCl? Here 0.1 molar and 1 molar are saturated. If potassium chloride solution is saturated with constant calomel, the electrode is called saturated calomel electrode. The electrode potential such as electrode as determined against the standard hydrogen electrode. If the KCl solution is exactly 1 molar, the potential is 0.2801 volt. This is sometimes called standard calomel electrode. Electrode potential of different types of calomel electrodes are given in the following table. The half cell reactions for this electrode is here Hg2 plus gaining of electrons, what we are getting Hg. It may be recalled that mercury is the dimeric species which are dealing with mercury, but ions in solution is Hg2 plus. According to that nernst equation, E is equal to E0 0.09591 by 2 log 1 by concentrations of Hg2 plus. Here Hg2 plus is also involved in another equilibrium. Hg2Cl2 is a slightly soluble salt for which may be write a solubility product constant Ksp. This is the typical laboratory made saturated calomel reference electrode. This is commercial calomel electrode. The silver chloride electrodes. Generally, the silver chloride electrodes, the silver wire is placed in thin layer of silver chloride solutions immersed in a solutions of potassium chloride of a known concentration. It can be represented by AgCl, KCl by Ac plus. The half cell reaction is written as AgCl gaining of electrons, what we are getting here, Ag plus Cl minus. This is what a typical silver chloride reference electrode, that is made by KCl solutions with 2 drops of silver nitrate solution, silver wire coated with AgCl is the porous disc. What is indicator electrodes? That indicator electrode of a cell is one whose potential is dependent on the activity of a particular species whose concentrations is to be determined. The several metals like that silver, copper, mercury, lead and cadmium that show reversible half reaction are used for the constructions of indicator electrodes. The potential developed are reversible and reflect the activities of these ions in solution. Among the metals, some metals like nickel, cobalt, tungsten do not give reproducible potential due to some chemical or physical reactions and hence are not used as indicator electrodes. This is the typical indicator electrodes design. The reactions involved in this equilibrium are AgI. It undergoes dissociation Ag plus I minus, Ag plus E minus gaining of Ag. Here, electrode potential of Ag is equal to 0.799 volt. Combining these two equations, what we are getting? AgI plus E minus gives Ag plus I. Applying nernst equations to the half reaction, we get the following relationship between the electrode potential and the anion activity. These are all mercury electrodes. In that mercury electrodes, the second order electrode used for the measurement of EDTA and its anions Y4 minus is based on response of mercury electrode in the presence of small concentrations of stable Hg EDTA complex. The half cell reactions for this electrode process are similar to the one given above the filter. For this electrode system, a small concentrations of HgY2 minus is introduced into the analyte solution. The complex is so stable that is the dissociation to form Hg2 plus is minimal and the concentrations of the complex remains constant over a wide range of Y4 minus. Hence the above equation may be simplified as this is the electrode largely used in complexometric titrations using EDT. That membrane or ion selective electrode. These are another category of electrodes called membrane or non-selective electrode. These electrodes preferentially respond to a single chemical species. The potential between the indicator electrode and the reference electrode varies as the concentration or activity of that particular species varies. Unlike the inert indicator electrodes, ion selective electrodes do not respond to all species in the solution. The glass membrane electrode or glass electrode is a typical example of ion selective electrode. Functioning and principle of glass electrode will be discussed in detail in that next unit. How to determinations of equilibrium constant. Determination of equilibrium constant. Calculate numerical values of many equilibrium constants such as solubility product constant, dissociation constant and formation constant. One important advantages of this method is that the measurement can be made without disturbing any equilibrium that may exist in the test solution. This is equilibrium constant. That equilibrium constant delta Z is equal to 0. Delta Z naught is equal to minus 2.3 RT log K. Delta Z is equal to minus NF E naught. Combining both above equation yield minus NF E naught is equal to minus 2.3 RT log K. Log K is equal to NF E naught by 2.3 RT. This is the summary of that unit. Let's go through that. Some important questions are mentioned here. The objective type question that is not asking in that examination. Next, What is that? These are short answer type questions. Please be good to that. Short answer type question. Distinguish between concentrations, polarization and kinetic polarization, galvanostat and amperostat, reference electrode and counter electrode. These are all important. This is all important. This is a long answer type question. Define electronegativity. Write the principle involved during electrolysis in a non-galvanic cell. Write the principle of electrode gravimetry without potential control of working electrode. These are all the very important things regarding that. Unit 12, the potentiometric titration. That potentiometric titration, just we know that already. What is potentiometry? Potentiometry is a classical analytical techniques with roots before 20th century. It is based on potential. It is based on the measurement of potential of an electrode system in the presence of magnitude of other substances. It enables the selective detections of ions. It is one of the electrochemical analytical method. Then, electric circuit is used to measure the current and applied potential created by the flow of charged particles. These are the things. The potentiometric titrations, it is a suitable indicator electrode is conveniently employed to establish the equivalence point for the titration. A potentiometric titrations provides different informations from the direct potentiometric measurement rather than involving absolute potential or potential with respect to standard offsets. The measurements are made while the titration is in progress. The equivalence point of the reaction will be revealed by a sudden change in potential in the plot of EMF readings against the volume of the titrating solution. One electrode must be maintained at a constant but not necessarily known potential. The electrode must serve as an indicator of the changes in ionic concentration and must respond rapidly. The solution must of course be stirred during the titration. This is the diagram of this potentiometric titration. Ordinarily, the titrations involves measuring and recording the cell potential after each addition of reagent. The titrant is added in large increments at the outset. At the end point approaching, the increments are made smaller. The sufficient time must be allowed for the attainment of equilibrium after each addition of reagent. The precipitation reactions may require several minutes for equilibrium, particularly in the vicinity of the equivalence points. What are the general principles behind that potentiometric titration? The Nernst equation tells us that measurable quantity, the voltage or potential, is related to the concentrations of species in solution. In many cases, the measured potential is due to the number of species and hence the concentrations of one can be difficult or impossible to determine. Electrodes have been designed to respond only to a species, thus allowing the measurement of its concentration. This is known as direct potentiometry and will be discussed in that next chapter. Just you see that this is the graphical representations of this potentiometric titration. Keep on adding into the titrant. Initially it is slightly increases. At equivalence point it is increases gradually. This is what end point. The wave-like shape occurs because of the rapid changing in voltage around the endpoint of the reaction. The endpoint break is the large change in voltage around the endpoint. The endpoint break should be large as possible to improve accuracy of detections. This is done choosing the titrant carefully. The endpoint volume is defined as the volume halfway up the endpoint break. The voltage values before the endpoint are due to the analyte. The voltage values after the endpoint are due to titrant. What are the locations of endpoints? In potentiometric titration, the endpoints is detected by determining the volume at which a selectively large change in potential occurs as the titrant is added. The method can be employed for all the reactions used for titrometric purposes: acid-bases, redox, precipitation, and complex formation. The titrations may be performed manually or the procedure may be automatic. In manual titration, the potential is measured after the addition of each successive increment of titrant, and the result readings are plotted on graph paper versus the volume of titrant to give the titration curve shown in the following figure. What are the types of the potentiometric titration? The majority of potentiometric titrations involve chemical reactions such as a neutralization, oxidation reduction, precipitation, and complexation. In that neutralization titration, potentiometric neutralization titrations are particularly useful for the analysis of mixtures of acids or polyprotic acids or bases because discriminations between endpoint can often be made. An approximate numerical value for dissociation constant of the reactant species can also be estimated from potentiometric titration curves in theory. This quantity can be obtained after any point along the curve as a practical match. This is the most easily calculated from the pH at the point of half neutralization. In the titrations of weak acid HA, we may ordinarily assume that at the midpoint, that oxidation reduction titration. The indicator electrodes for oxidation reduction are generally fabricated from platinum, gold, mercury, or silver. The metal chosen must be unreactive with respect to the components of the reaction. It is merely a site for electron transfer. Platinum electrode is most widely used for oxidation reduction titration. It should be recalled that the curves for many oxidation reduction titration are not symmetric. The equivalence point potential may be significantly different from the potential corresponding to the point of inflections in the curve. This is oxidized form, gaining of electrons, we are getting a reduced form. The potential acquired by the indicator electrode at 25 degrees Celsius is mentioned here, where E0 is the standard potential of the system. The potential of the immersed electrode is controlled by the ratio of these activities or concentration. In redox reactions, reducing agent is oxidized or oxidized agent is reduced, and the ratio and the potential therefore changes more rapidly at the end point of the reaction. What are the precipitation titration? The titrations involving the precipitation reactions are not nearly so numerous in titrometric analysis, perhaps those involving redox or acid-base reaction. One of the reasons for limited use of such reaction is the lack of suitable indicators. In some cases, particularly in the titrations of dilute solution, the rate of reaction is too slow for convenience of titration. This is representations of this precipitation titration by potentiometric titration. This is differential titration. That differential titration, this titrations requires use of two identical indicators electrode, one of which is well shielded from bulk of the solution. Just to see that figure here, this is the magnetic stirrer, this is the indicator electrode, the side arm test tubes, small hole, this is the rubber bulb, this is the burette, keep on adding into that titrant. Here one of the electrode is contained in small side arm test tube. Contact with the bulk of the solution is made through a small hole in the bottom of the tube. Because of the restricted access, the composition of the solution surrounding the shielded electrode will not be immediately affected by an addition of titrant to the bulk of the solution. The resulting difference in solution composition gives rise to a difference in potential delta E between the electrodes. After each potential measurement, the solution is homogenized by squeezing the rubber bulb several times. Upon delta E again becomes 0. If the volume of the solution in the tube that shield the electrode is kept small, the error arising from failure of final additions of reagent to react with these portions of the solutions can be shown to be negligibly small. The main advantage of a differential method is the eliminations of the need for reference electrode and short bridge. The automatic titration. Nowadays, large number of automatic titrators based on the principle of potentiometry have come into the market. These are highly useful in those places where a large number of routine analyses are required. These may not be more accurate than the manual techniques, but are quite rapid and decrease the time needed to perform the experimental and thus offer some economic advantages. The two important automatic titrators are available here. The first type gives titration curves of volume versus EMF. Here delta E versus delta V. The endpoint is obtained from the curve by inspections. In the second type of titration, titration is stopped automatically when the potential of the electrode system reaches a predetermined value and the volume of reagent delivered is read at the operator's convenience or printed on a tape. These titrators usually employed a burette system with a solenoid operated value to control the flow, or alternatively it makes use for a syringe, the plunger of which it is activated by motor driven micrometers. This is the summary of this unit. In this unit, we have to learn about the electrode potential, principles of potentiometer and measurement of potential, different types of reference electrodes such as hydrogen electrode, calomel electrode, silver chloride electrode, different types of indicator electrodes. And you have also learned about the measurement of potential and location of endpoints from the graphs obtained from the experimental values of EMF and volume of titrant, different type of titration such as acid-base titration, redox titration, precipitation titration, complexometric titrations and differential titrations were also explained in that detail. Okay. These are all self-understanding questions. Why the absolute value of electrode potential can be determined. What is reference electrode? Give some example. Explain liquid junction potential. How can it be eliminated? What is the standard cell? Give the reaction in case of distance standard cell. These are all the important questions. Please be good. Thank you, Anada.